we're going to finish off looking at our graphs and inequalities by looking in a bit more detail at asymptotes. Asymptotes. Okay, so when you are drawing your curves of course always bend towards the asymptote. Okay. They will never cut a vertical asymptote. But they can cut oblique or horizontal ones. And this is one of the misconceptions people often have. They think you can't cut any asymptote at all. It's only the vertical ones they can't cut. Because your horizontal and oblique, basically it's just telling you what's the curve doing out of the extremities, out at plus or minus infinity. So around 0, or compared to infinity, 1,000 is close to 0. So around 0, it can cut the asymptote because the horizontal or the oblique asymptote has no meaning around the origin. It's what's happening out at the extremities. This basic polynomial idea. So if you're drawing a graph which is a polynomial on a polynomial, do a polynomial division, and then the asymptotes are very easy to find because what happens is the bottom of the fraction, same as normal. That tells you where the vertical asymptotes are going to be. Solve that equaling 0. The quotient when you do the division, that will be the oblique or the horizontal asymptote. Okay. And the remainder on top will tell you if it cuts it. If you solve that numerator equals 0, then if there is a solution, then that is where it will cut the oblique or the horizontal asymptote. So let's just use this one as an example. I've got it all factorised out, but if I did the polynomial division on that, the numerator turns out to be x squared plus x minus 6. The denominator is x squared minus 1, so I'll end up with 1, remainder of x minus 5, so I can rewrite it as 1 plus. Now looking at it in this form, okay, I know it's got x-intercepts, so I'll go back to the first one for the x-intercepts because we solved y equals 0. And when you've got a fraction equaling 0, of course, it's the top of the fraction that equals 0. So our x-intercepts will be at minus 3 and positive 2. The y-intercepts are always easy to find. That's just sub x equals 0 in. Turns out to be 6 on this one. So looking at the bottom of the fraction, I've got vertical asymptotes at plus or minus 1. So we'll just draw those in. There's a horizontal asymptote at y equals 1. But in this case, it will cut the horizontal asymptote at x equals 5. Okay? Because if you look at it, it is possible for this function to equal 1. Right? So therefore, it must cut the horizontal asymptote over there at 5, 1. Now, the curve always has to bend towards the asymptote. It can only go through the points that we've just talked about. So if we look at it logically, we get the shape. If I get here at the left-hand side, it's got to go through minus 3. It's got to bend towards this asymptote, bend towards this one. So we must have some sort of hyperbolic shape. Oop, like so. Over on the, which one? I'll probably do the middle bit next. Here we've got 6. Now there's two things I suppose it could do. It's got to bend towards these asymptotes. So I'm going to have a U sort of shape, maybe. I might have an inflecting shape. But we know there's no x-intercepts in between minus 1 and 1. So therefore, it can't come down from 6. So we must have a concave up sort of shape, like so. Only thing it could possibly do. Now over here, it's got to bend towards this asymptote, cut through 2, but I now know it actually passes through 5. But when it passes, it's got to come back to the asymptote. So at some point, it must turn, come back down, and bend towards the asymptote. Well, a little bit dodgy drawing, but you see what I've tried to do there. I've gone through 1, 5, 1, and turned and come back through. So that's sort of what that graph would look like. Okay, this one's a little bit more involved. Again, if I do my polynomial division, we end up with an oblique asymptote this time. X minus 1 will be the asymptote. And the remainder is 4x minus 4. So that's how we break this one up. So same sort of idea. I can look at the original for the x-intercepts. I've got -1, 1, and 2. Y-intercept turns out to be -1/3. Vertical asymptotes at -2 and +3. So put those in. This time I've got an oblique asymptote at y equals x minus 1. So I'll put that one in. Yes, it does cut the, well, I've written horizontal, but of course I mean oblique asymptote. And it will cut it at x equals 1, because that would solve the top of this fraction. So, and if you look at my graph, I kind of knew that already, because we'd already decided that there was an x-intercept at 1. All right, let's draw this one in. Over the far left-hand side, I've got no x-intercepts, but I've got these asymptotes. So I must be in this little triangle down the bottom. I must get a sort of, well, it's not a U, but some sort of bendy shape, whatever we call that. It goes towards those asymptotes. On the far right-hand side, that'll probably be the next easiest bit to do. Same thing. I haven't got an x-intercept past this asymptote, so I must be contained in the top triangle there. Did I do that bit next? No, I didn't. Okay. So the bit in the middle, I've got to go through -1 and -1/3. I've got to bend towards y equals 2, x equals -2. So I must have come from up here. It would have been possible to come from the bottom, go through -1, and then somehow get back to -1/3. There's no x-intercept there to go back to it. So my only possibility is I came from the top, came down, then I could go through -1/3. I can pass through the other x-intercept. I must turn, and I know I turn underneath y equals x minus 1, because we've determined it only cuts that asymptote at x equals 1. And then come back down, bend towards my asymptote. And then to finish it off, there we go, in that triangle bit there. So just by finding these asymptotes, we can get a reasonably good sketch of some of these more interesting graphs. It's all right. Have a go at a few of those. Exercise 3.